So to finish Chapter 10, we're going to use data from the book, which is Chapter 10, Problem 31, the Gender and Social Networks.jump dataset. A university professor wanted to investigate the social habits of students at her school. She took a random sample of students and asked how many hours per week each spent on social networks, as well as the gender of each student. Now, for the purposes of this example, students had to respond whether they were male or female, even though in reality gender is fluid and non-binary. Now, the question we're trying to answer is whether there's an association between gender and time spent on social networks, which is really the same thing as wanting to predict the amount spent of time spent on social networks for each gender. And we want to know, can we do that? And so if we were doing this using a regression model, that model would be mu equals alpha plus beta x, where x is an indicator variable, and we could define that to be 1 for females and 0 for males. And then we would have to therefore define our separate parameters, where mu, as before, is the true mean response, where in this case the response is time spent on social networks. And that's conditional, right? So it depends on the value of x. So it's the time spent on social networks for a given x. Alpha, as before, is an intercept, so alpha is the true mean time spent on social networks, but specifically when x equals 0. But if x equals 0, that means the student is male, so we can contextualize it further. It's the true mean time spent on social networks for male students. And then finally, we would define beta. And beta here looks like a slope, so it's going to be the true mean change, or the true change in the mean time spent on social networks. But the change for what? The change for a 1 unit increase, and 1 unit means from 0 to 1 in this case, so that's the true change in the mean time spent on social networks from males to females, or for females versus males. So that is, if there's a difference in the time for male and female students, then beta would not be 0. And if they're the same, then beta would be 0. So if a student equals female, or excuse me, if a student is female, that is if x equals 1, our model will be mu equals alpha plus beta times 1, which is just mu equals alpha plus beta. But we can see that this is two constants, a true change and a true mean time. So we can see this is just mu for female students. Similarly, if the student is male, if x equals 0, mu equals alpha plus beta times 0, and that would just be mu equals alpha. We've already seen this. Alpha is the true mean time spent on social networks for males, so that would be mu male. And so the only difference is beta. So beta is the difference in time that females and time that males spend on social networks. So we could look and see, is beta equal 0? But we could also then see just are mu female and mu male the same. So if these are the same, then beta equals 0. And if they're different, then beta is not equal 0. Graphically, based on our sample data that's in the data set, we want to know, is this a flat line? Or is the line not flat? If it's a flat line, then beta equals 0 in the population. If it's not a flat line, then beta is not equal 0. That means there is a difference in the means. And so we can think about this slope, right? But really we've got this value here and this value here. So 0 here is male, 1 here is female. And so this point that the line is connected to, this is our sample mean for female. And this point here, this is our sample mean for male. So we could look and see, is there a difference between the two, looking at the slope of this line, B. But it's a lot easier just to say, does y bar female equal y bar male? Just compare the 2 points directly. But if they are equal to each other, that's the same thing as saying b, the slope of that line, equals 0. The line is flat. And we can see that the line is not flat. The line is never going to be perfectly flat because we don't have perfection in our data. There's always variability in our sample. So really we want to know, is the line close enough to 0 to fail to reject our null hypothesis, or is there enough difference? Is the line different enough from completely horizontal for us to believe that, yeah, males and females differ in their usage of social networks? So let's further summarize this. So we have our descriptive statistics. So we have our mean for females. This is 15.61, and we can see that there are 21 women in the sample. We also have our descriptive statistics for males, and the mean there is 11.91. So the averages are not exactly the same. They're similar, but they're not the same. But then we also see that there's variability around those averages. And that means that the difference is going to have variability too. We're not always going to see this exact same sample difference of about 3, right? And that variability is going to change from one sample to the next because of these different sample sizes. So let's look at those models again. If a student equals female, or a student is female, that is if x equals 1, mu equals alpha plus beta. This is a constant. That is, mu equals alpha plus beta equals mu female. If a student equals male, then again, we know mu equals alpha, that's mu male. So we want to know if there's a difference, mu female minus mu male, in the amount of time spent on the social networks. We want to know, is there a true difference in means? If there were no difference, what would the model be? The model would just be mu equals alpha. Beta would be 0. That is, all students, regardless of gender, would have the same mean response. That would just be mu, which would just be alpha. We could write a null hypothesis, therefore, this way. Mu1 minus mu2 equals 0, versus mu1 minus mu2 does not equal 0. And we would define mu1 and mu2. In this case, mu1 is the mean for males. We can be specific and say it's the true mean for males in time spent on social networks. Similarly, mu2 is the true mean time females spend on social networks. Now, the next bit of the set in the notes we've already completed, right? So we've already filled out the general format of a two-sample test for hypothesis testing. So what I'm going to do is I'm going to come down to where we have to complete the social networks hypothesis test. So we want to test whether male and female students use social networks for the same amount of time on average, and we're going to use alpha equals 0.1, right? And so this is where we have to read carefully and make sure that we are using the correct alpha as provided and not just always going to the default. So the first step in any hypothesis test is to state our hypotheses. So our null hypothesis is that mu1 minus mu2 equals 0 versus the alternative mu1 minus mu2 does not equal to 0. And we're going to use equals to 0 in the null because if this is 0, this is the same thing as saying beta equals 0, that there's no difference or that there's no association between gender and the usage of social networks. And that would be like what we saw before, that there's just that horizontal line, that there's no change between one gender and the next and the amount of social networks that they amount of time that they spend on social networks. The alternative, we want to know if they use social networks for the same amount of time or not. And so we don't care who uses social networks more or who uses social networks less. We just want to know if there's a difference. So that's why we're going to make this a two-tailed test. And again, like we saw when we first identified our hypotheses, we're going to define our two population means. And we can do this in one sentence. So we're going to say where mu1 and mu2 are respectively the true mean time spent on social networks for male and female students. And we can be even more specific and say for students at this particular school because of the student sample was taken, but we'll limit ourselves to here, right? So you don't have to define each parameter separately, just like when we were talking about slopes and multiple regression. We can do this all in one set, all right? To test this, we have two samples, a sample of male and a sample of female students. So this is a two-sample t-test, right? Whenever we're dealing with a quantitative response in this class, we're going to do a t-test. And because we have independent samples, we could also refer to this as an independent samples t-test. So either of those are fine, but the important part is we are doing a t-test for two population means. For this test to be valid, we have 5 conditions we need to satisfy. The first is that we have random samples, and that's to achieve unbiasedness in the population, or unbiasedness of our estimation of our population parameters. We also need our samples to be independent, and that is achieved when no one in one sample is measured twice by being also in the other sample. And we talked about how to get dependent samples in class. We need a quantitative response and a categorical predictor. So we have a quantitative response because the time spent on social networks is quantitative. We can take the average of time. And we have a categorical predictor because we're treating gender as categorical. You're either male or female in this example. We also need that the time spent on social networks is approximately normal for both populations. So the time that males spend on social networks is approximately normal, and the time spent on social networks for females is approximately normal. And we check that by looking at a histogram for both males and females. So if in our sample that time looks normal, or is unimodal and symmetric or approximately bell-shaped, then it's reasonable to assume that it's approximately normal in the population, as long as we have a random sample. And then finally, normally, if we're just thinking about what the conditions are most broadly, we'd say something about the sample population standard deviations. But now that we have our sample statistics, we can actually do a check for what we're going to assume about those standard deviations. And in this case, we're going to assume unequal population standard deviations. So that would be sigma 1 does not equal sigma 2. Now why is that? If we go back and look at our sample data all the way up here, we can see that our standard deviation for group 1 for males is 3.94, and our standard deviation for group 2 is 7.996. And so if we do S max over S min, that's going to be 7.996 over 3.942, and that's just bigger than 2. And if you're like, well, you know, Megan, that's basically 2, we can also see that our sample sizes, N1, is very different than N2. So even if you're like, 7.996, that's basically twice 3.94, that's good enough to assume equal standard deviations. Our sample sizes are so different, we still are going to use the unequal standard deviations assumption. So we come down here and we have to justify why we're using unequal standard deviations. We can't just say it. We always justify it, and I've gone too far. So we say because 7.996 over 3.942 is greater than 2, and you can say and n1 is much greater than n2. Or excuse me, n2 is much greater than n1. Okay? So those are our 5 conditions, and now we can go on to our mechanics. The first step in mechanics is always to identify our significance level. We're told that we're going to use alpha equals 0.10 or 10%, so this is provided, right? So this is where we have to read carefully and not just plow through on autopilot. And that means we reject the null hypothesis if we get a p-value less than alpha of 0.10. Our t-test statistic, t-obs, is always of the form observed minus hypothesized over the standard error. Well, we're estimating a difference in population means, so we observe a difference in sample means. So that's going to be y1 bar minus y2 bar. I can write that a little bit neater. Minus y2 bar divided by the standard error of that test statistic, that observed sample statistic. If we were to scroll back up, we would see that the sample mean for males is 11.917. The sample statistic for females is 15.619. And the standard error, well, because we were assuming unequal population standard deviations, our standard error is the easy one. It's the square root of s1 squared over n1 plus s2 squared over n2. So we can plug in now. So we've got negative 3.702 for that difference in the numerator. And then for our standard error, this is going to be the square root of 3.942 squared over 12 plus 7.996 squared over 21. And that gives me a test statistic of negative 1.777. So that's not huge. Usually we're looking for things greater than 3 or less than negative 3, but it's not small. We've observed something, our sample difference is about 1 3/4 standard errors away from the hypothesized value. So this is why it's useful to find a p-value, because it tells us how unusual something is if the null were true. So now we can find that p-value. And our p-value is going to be the probability that we observe, or that we get a t with some degrees of freedom that is greater than, because this is a two-tailed test, that is greater than this absolute value of our test statistic. So that is something that is more than 1.777 standard errors greater than, and more than 1.77 standard errors less than 0 from this t. But the issue is we need our degrees of freedom. So I'm going to come over here and calculate our degrees of freedom. So we got away easy with the standard error, but because of this unequal standard deviations assumption, our degrees of freedom is found using that welch-satterhwaite approximation. So our degrees of freedom, we have to use that really heinous looking thing. So we're going to do s1 squared over n1 plus s2 squared over n2, and we square that whole thing. So it's a variance over its sample size plus the other group variance over its sample size, and then square that whole sum. And that's just the numerator. And then the denominator, we have 1 over n1 minus 1 times this thing squared again. So s1 squared over n1, and we square that, plus we do the same thing for the other group, 1 over n2 minus 1, and then times s2 squared over n2, and we square that little ratio. And that whole thing we round down. So now it's just a question of carefully plugging in our values. S1 squared was 3.942 squared, N1 was 12. S2 squared is 7.996 squared over N2 is 21. We square that. That's our numerator. The denominator is 1 over 12 minus 1 times 3.942 squared over 12. Square that. And then we do the same thing for group 2, 1 over 21 minus 1 times 7.996 squared over 21. Square that. Round that down. When we do all this math, and do this very carefully, very slowly, if you want, I would work out maybe this numerator, and then maybe this part of the denominator, and then this part of the denominator, and then pull those three pieces together. But when you've done that, you're going to end up with the floor of 30.572 or something very close to that, depending on when you round and where you round, right? And this is all approximate. So our degrees of freedom are approximately 30, because remember, this means round down or truncate, because we were dealing with whole numbers. So we're going to use 30 degrees of freedom to find our p-value. So now we can go over to JUMP and get our p-value. So if we're doing this by hand, that is if we're not having JUMP calculate things for us, we will go to our add-ins, teaching modules, distribution calculator. We go to the T distribution and we put in 30 degrees of freedom because that's what we just calculated. This is quite a bit less, well, not grossly less, but this is definitely less than what we would have done if we had used the degrees of freedom for error, the n1 plus n2 minus 2. We have our value and we're trying to calculate a p-value, a probability. So we're not going to change the type of calculation. But we do want a two-tailed test. So we don't want either of these first two, and we want the two tails, so we pick this last option. And then we're going to just put in our test statistic. The negative value for the first one, so negative 1.777, and then the positive value for the second one, 1.777. And we can see that it's shading in the tails. So the value that results, 0.0857, that is our p-value. So all that work for just this one little probability, 0.0857. Whew, I'm exhausted. How do you feel? All right, so now we can get our conclusion. Because our p-value is less than, oops, we should say what our p-value is. Our p-value of 0.0857 is less than alpha of 0.10, right? So remember, we're using alpha of 0.1, not alpha of 0.05. We can reject the null hypothesis. That means there is sufficient sample evidence to believe that male and female students spend a different amount of time on social networks on average. And this on average is important. if we look at this plot, we can see that there is a fair amount of overlap between what male students are doing on social networks and the amount of time that female students are spending on social networks. It's only that there's a difference in the average amount of time. Some female students are spending very little time on social networks, and some male students are spending a fair amount of time on social networks. It's just that the difference in the average amount of time is not the same, is not zero. That's what we're testing. Not whether all males and all females are spending a different amount of time, just whether the average amount of time is different. And that's why we have to be very careful in how we communicate our results. So even though we have sufficient evidence that there's a difference in the average amount of time that male and female students spend on social networks, we can't say who spends more time, right? We don't have the results, or we don't have the ability to say that statistically, because we didn't do a one-sided test. With a two-sided test, we can say there's evidence for a difference or there's not enough evidence for a difference, but that's as far as we can go. That's why sometimes we prefer a confidence interval, because if we have evidence for a difference, that means the entire range of plausible values gives us evidence of, where that difference lies. So, remembering that every confidence interval is always of the form point estimate plus or minus critical value times the standard error, we're going to use the point estimate of y1 bar minus y2 bar, right? The same point estimate as in our hypothesis test. So this was just the numerator of our test statistic. And we're going to use the same rule for identifying our standard error. So if the ratio of max over min is less than 2, we'll use the pooled. And if S max over S min is greater than 2, we'll use the easy standard error. And then the critical value is going to be found using the same rule as well. So because we still have to identify the degrees of freedom. So if S max over S min is greater than 2, we'll use the welch-satterhwaite approximation. But if S max over S min is less than 2, well, because we use the pooled standard error, we're going to use the degrees of freedom for error, because this is basically a regression assumption. But we already identified S max over S min is greater than 2. So we used the easy standard error, but that means we had to use the welch-satterhwaite approximation. So that we already did. We found the degrees of freedom to be approximately 30. So we're going to find and interpret a 90% confidence interval for the difference in the amount of time spent on social networks for male and female students. So in this case, our point estimate was y1 bar minus y2 bar. And so y1 bar, that was the sample average time for males, and that was 11.917. And for females, y2 bar was 15.619. This sample difference, the numerator of our test statistic before, is negative 3.702. And this is in hours. So we can remember our units this way, because it's the average amount of time, so this is the difference in the average amount of time. Our critical value, this is going to be a T star with some degrees of freedom. But we know that our degrees of freedom is 30, and this is because sigma 1, because I can't write, because sigma 1 is not assumed to be equal to sigma 2, right? So we used the welch-satterhwaite approximation. So here's the nice thing. If you've already done that approximation to calculate your degrees of freedom, I'm not going to ask you to do it again. Do the work once, but show the work. All right? And so we would then go to the jump distribution calculator, and we would find this to be 1.697. How do we do that? Well, we go to the jump distribution calculator, the same one that we used to find our p-value. And so we go to the t-distribution. It's still 30 degrees of freedom, but now we input our probability to calculate our critical value. We want a central probability, and we want a 90% confidence level. So we put in 0.9 for the probability. And that's where this 1.697, or if you want to use all 4 decimal places, 1.6973 comes from. So our critical value is found the same way we always do. We go to distribution we want, we enter the parameters, we input the probability. That probability is our confidence level to calculate our critical value. And then finally, the standard error for our confidence interval, this is the same that we had for our hypothesis test as well. So because we assume unequal standard deviations, this is going to be the standard error of y1 bar minus y2 bar, and this would be the square root of s1 squared over n1 plus s2 squared over n2. And we found before that this is 2.8315. This is the same as for the hypothesis test. So this is the same point estimate as for the hypothesis test. This is the same degrees of freedom for finding the p-value for the hypothesis test. It's the same standard error as finding the test statistic for the hypothesis test. So confidence intervals and hypothesis tests, they use the same things. The only thing that differs is that we use a critical value to find how far away we need to go, and for a hypothesis test, we calculate a test statistic. Right? So for a confidence interval, we have a probability, and then we calculate. We have a probability, and we use that to get a t critical value. A hypothesis test, we calculate a t value or test statistic, and we use that to find a probability, our p-value. All right? So now we have all the things we need. So we're going to do point estimate plus or minus critical value times our standard error. So we have PE plus or minus CV times SE. Excuse me. So it's negative 3.702 plus or minus 1.697 times 2.8315. And that gives us negative 7.237 up to negative 0.1667. This does not contain 0. So this is consistent with what we found in our hypothesis test. I do not believe that 0 is a plausible value for the difference in mu1 and mu2. But the whole interval is negative. The whole interval is less than 0. So that means that I believe that mu1 is less than mu2 at 90% confidence. It doesn't mean that this is guaranteed. It doesn't mean that these answers or these conclusions are correct. It just means that based on my current evidence, these are reasonable things to believe. All right? So let's actually write our conclusion, or our interpretation. With 90% confidence, the true difference in means, or excuse me, in mean amount of time spent on social networks for male versus female students is contained by the interval negative 7.237 to negative 0.1667 hours. And because this interval contains that true difference with 90% confidence, I'm willing to believe that a difference exists. I'm willing to believe that males spend less time than females on social networks, on average. And that's all I wanted to do. The important part was for you to see how to calculate the standard error. The important part was for you to see how to use this welch-satterhwaite approximation to get these degrees of freedom. So I hope this helped clarify some things, and good luck.